My name is David Flynn. I am the CEO of the company Hammerspace. But you might know me from my previous venture, which was the company Fusion.io, introduced the first PCI Express attached flash, what later became NVMe. But hopefully you'll find what we're talking about today interesting. Let me offer that you're welcome to raise your hand and ask questions along the way. We can save questions to the end too. We'll have a room for that. I think we have a good amount of time today, so we'll be able to go into some detail. And happy to answer questions along the way and can help direct some of the discussion. But all right, so we're going to be talking here about NFS. But this is not your grandma's NFS. As one of my customers, one of the big hyperscalers that has never had NFS in their production data centers where they have literally hundreds of thousands, if not millions of servers. He said, we've not got any shared file, and all of a sudden we need it for our AI workloads. And it's interesting that the principal engineer there said that we're on a mission to make NFS great. He said make NFS great again, but then he corrected himself and said it's never been that great. NFS has always come with a mixed bag. We're going to talk about some of that and how it's changing along the way here. And we're going to talk specifically about parallel NFS, maybe a little bit about what that means and how it's different from traditional NFS, what it takes to build an enterprise NAS system using this newer NFS technology. What are some of the results from a performance perspective? And then maybe a little bit about some of the customers that are using this today. So without further ado, let's jump in. The first thing is to talk a little bit about the market dynamics that we live in today and how things are different. And one of the two, let me go ahead and jump to the second one too here. Two of the most interesting things is that HPC is no longer as much of a niche as it was. It's becoming very mainstream with AI and ML being all of the rage that it is and the need to feed data in massive parallel into a bunch of GPUs to do training and other things. We're seeing almost every company at scale, of a reasonable scale, investing large in doing AI types of workloads. And that needs sort of the twin things that are typically difficult to get together, and that is very high performance delivery of data into the computers, and also the requirement for data to be extracted from the silos and made available in different locations. I like to think of it as, in the olden days, you had your application with a sort of a one-to-one relationship with the storage. The application's data set went on a specific piece of storage. Life was good. That's your data warehouse, your transactional system, whatever. But in this world with AI, we now need the data set from every application available to many different models, and we need to work on that in many different physical locations. So we went from a one-to-one relationship to a many data sets to many models, and doing the training work in many different facilities. Because it's a very bursty workload, you really need to be able to tap into shared infrastructure, i.e. cloud, and often many different regions or even many different cloud providers because of the challenge of finding availability. So we've gone from a one-to-one relationship to a many cross-product relationship, and that drives the need for data to now not be localized just to the storage system. So data orchestration is an important need, and high performance is an important need. And those two things typically work against each other. One is at the macro scale, moving data sets between data centers, between storage systems, and the other one within the storage system. At the same time, we live in a reality where at scale it needs to be software defined. It's not as tenable to put dedicated storage system infrastructure in very large scale within the cloud infrastructure, or organizations large enough to build their own infrastructure are going to want to run it in a cloud-like fashion, which means they're going to want to use commodity off-the-shelf servers. And they're going to want to use a software overlay to be able to get the file serving environment from that. So that's one of today's realities, is that working in a software defined on commodity. But there are some things we can count in the assets column. If the first set of things are the demand drivers, the needs, one of the things that we have at our advantage is that Linux has won the Unix wars and pretty much won the data center war as well. And what that means is that there's really only one NFS client where innovation matters. Yeah, NFS v3 under ESX or under your old OSs, that's great. It doesn't need to change. It's good enough. It's fine. But in terms of innovation, to give high performance and so forth, Linux is where it's all at. That was never the case before. You needed many different NFS clients to all be largely compatible with each other. And now that's not the case. It's really only the Linux client that matters, which allows us to put more sophistication into that client and more nuance into the protocol, things that are harder to implement and get bug compatible, because forget making it bug free, you just want to make sure it operates the same. So Linux being ubiquitous is a huge help there. And this is the environment in which NFS 4.2 has been standardized to help address these exact problems. NFS 4.2 largely came from the team here at Hammerspace. And what we did was we took the, I would call them the more academic, call it a first pass implementation of parallel NFS that came in much earlier, and made it into something that can be used as enterprise NAS. Because what it was a bit of an academic thing and not really something capable of being production reliable to be a true enterprise NAS. And even then, it was highly fragmented. At the heart of parallel NFS was that you have different types of layouts. You have a block layout, you have a file layout. The flex files layout, which we introduced, is the only one that doesn't need anything specific on the back end. Just anything that speaks old NFS v3 can be a storage node. And that's the first time that was the case. So NFS 4.2 is somewhat unique in that it wasn't kind of co-opted by the hardware vendors to do something that's specific to their storage systems. It's designed to be able to work generically across anything that speaks NFS v3. Is a storage node in the bigger system. So with 4.2, we can solve these problems. We can allow data to migrate freely behind the scenes while the namespace is continuously available and serving data, even while data is moving between systems or even between whole data centers. So it can solve that data siloing problem. And it is, of course, inherently a parallel file system. So it really can solve these twin problems of data orchestration, the localized nature of data. It allows you to delocalize the data to make the data's access and consumption and even its preservation independent of the storage system storing it, because now it can move freely across them. But then it also can serve the data at the highest levels of performance as a true parallel file system architecture, which we'll delve into a little bit more. And it avoids the need to have to rewrite applications to talk HTTP REST from user space. Object storage, well, in its very name, S3, super simplified storage, it was, in essence, a dumbed down file system for the purpose of getting to global scale. So Amazon, faced with wanting to host a whole bunch of different companies with a whole bunch of data, multi-tenancy, we know how hard a problem that is. They said we got to build something scalable enough, and file systems are really hard. POSIX semantics are difficult, and they don't scale very well, especially when you don't have parallel NFS. So they threw out the baby with the bathwater, and they convinced the entire industry that the way you do cloud is you write everything to talk REST from user space, and you forego having the convenience of your operating system actually knowing how to natively consume data from the thing. Consider how silly that is. It can't even host your binaries or shared libraries. It can't host even the software stack that you're going to run from, because the OS can't demand load stuff out of it. And but you know, they did a good job of convincing the industry, and what else convinced is that object storage is very cheap, because building file systems is hard, but building object storage is not as much. It's easier to get object storage at a lower cost. Even today, object storage in the cloud costs 1/20th as much on a per capacity basis as file storage. So there's a premium paid, which also speaks to the value of actually having a true POSIX interface. But it's still the traditional wisdom that to get to scale in the cloud, you need to bite the bullet and rewrite everything to use object storage, because file doesn't scale or whatever. But the truth is that AI workloads, once again, are changing the dynamic, as I was alluding to in the beginning. Even these huge hyperscale companies that have had large homogeneous applications. See, you can afford to rewrite those because they're so big, you get a lot of leverage from doing it once, right? So the big web properties did what they could do to get the most efficiency and cost structure. And that was to not use file interfaces, to use object interfaces. But when you have AI workloads and you need your researchers to have home directories within which they can manipulate petabytes of data and then run applications across a cluster that are feeding off of that, you need true POSIX interfaces, right? You're not going to do the classical HPC supercomputing from object storage interfaces without first copying it out and staging it in something that talks file. So this NFS 4.2 allows you to do file at cloud scale, which was not possible before. So let's talk a little more specific, because this is all great in generalities, but what are some of the actual things? And you know, we're going to get a little technical here. You're welcome to ask questions along the way. Helps me gauge how interesting this is or isn't, how much time we should spend on it. But the first thing that we did in the 4.2 spec and in the open source implementation is did everything possible to get rid of the chattiness that we're all familiar with in network file system protocols. SMB suffers from it too, NFS does as well. But the more exotic HPC file systems have gone to great lengths to avoid excessive round-trip chatter on the wire. And with 4.2, we had a chance to kind of fix this. Now, let's talk about where it originated. It originated, did anybody here work for Sun back in the day? Do we have any former Sun folks that, oh, wow, yes? Well, the dogma around statelessness is what led to it initially being chatty. It's a great idea, especially given the complexity of managing state, that they made the protocol stateless, but that meant it had the attention span of a fish. It had to go back and ask all the time, oops, has it changed? Oops, has it changed? Before I actually use it, oops, has it changed? So to do a simple file create and write the file, it takes 3 round trips. For it to do the create, make sure it didn't race, and then to send the data. And then for another program on the same exact client node to turn around and read that file, it takes 2 additional round trips. And the thing about all 5 of these round trips is they are all serialized. It has to wait for the response for the one before it even sends the other. Now with NFS 4.2, you have the ability to do compounds. You can send a request with another request and another request all in one packet, even referring to the results of the first in the second and in the third. So you can build a chain, a command chain that does something more sophisticated. These compounds allow you to send down a whole slew of requests that get something done. And so compounding is one of the most important capabilities to reducing round-trip chatter, but also caching and delegation. So basically, get rid of the statelessness dogma and instead say, we're going to cache state on the client. The client's going to remember some stuff, and by remembering stuff, the server has to remember that the client has it and be able to make callbacks and ask the client for it to come back. So if we're going to have state in the client that is authoritative, now you have to have the server know about that and be able to make callbacks to the client. So the other thing is the protocol is no longer a one-way protocol, the client making requests and getting responses. Now with statelessness, you have to make it a two-way protocol where the server can make requests of the client, say like, I've got this other client that wants something, you have the definitive state, you need to give that back to me, or at least tell me what the answer is so I can give it to him. So the protocol was made much more sophisticated, a two-way protocol, a stateful protocol, and all of this makes that the client much more complex, which goes back to the fact that Linux won the Unix wars, and when you're talking about high-performance shared file, it's really the only OS that matters anymore in the data center, so it allows us to put more sophistication into the spec and into the implementation. Of course, one of the things that greatly helps here is that our CTO is Trond Mikkelbust, the kernel maintainer of the NFS client. So the reason we've been able to do this is because he's the guy over the last 20 plus years who basically wrote most of the NFS client as it exists today in Linux. And so he was able to add these sophisticated, complex capabilities, which in the world of exotic parallel file systems, it's in that client that you would have to deploy on your servers, right? You'd have to put that GPFS client there, or you'd have to put that Luster client there, or you'd have to put that Weka client on there to get any kind of performance. Now what we're saying is that the NFS client has actually been able to get the care and attention to have the sophistication to do that stuff out of the box. And this has been capable all the way back to RHEL 7. Time frame. So basically anything that's in mass deployment now already has built into Linux enough to do this parallel NFS stuff, because Trond and the team here had already pushed enough of that upstream many years ago for it to have trickled back in. And what this does is it gets rid of 80% of the get attribute traffic that you see. But the most quantifiable way to talk about it is it really gets it down to the logical minimum, the extreme, of creating a file and writing it takes one transaction to the metadata server and then one transaction, if the write fits in one buffer, to the data storage node where it goes direct. So it's 2 round trips. And then the subsequent read doesn't even have to go off box because he's cached enough, not just the data in the page cache, but the metadata is delegated. So now he can open and read it without even having to go and ask permission for it of the server. In other words, it takes those 5 round trips down to 2. Now, how many of you are familiar with NFS 4 and the abortive attempts to shift to use NFS 4? If you have tried it, you've probably seen it's way slower. It's much chattier. The 5 round trips that NFS 3 would take, on NFS 4, they added a lot of the sophistication, but didn't really, it was a retrofit, both on the client and the storage systems that attempted to use it. And because of that retrofit nature, you didn't really take advantage of the statefulness, and instead you got all of the disadvantages compounding on top of the statelessness. So think of it as taking the worst of both worlds. It's the worst of stateless and the worst of state. And that's why it would take 15 round trips just to create and write a file to have another program pick it up and read it. That, by the way, is like a classic compiler workflow. The compiler reads a C file, writes an O file, reads the O file, and links it. So the linker phase. And it's crazy that it would take 15 round trips, serialized. That, by the way, is why you can't use the protocol very well over any kind of distance of latency, because of so many round trips. Any questions here about this work? I view this as some of the most important work that's been done to make NFS great. And I'll leave off the again, yeah.
So this is nothing to do with parallel NFS, right? So
this has nothing to do with parallel NFS yet.
You said parallel file system refers to, at least in traditional file system, a single file is at least spread across multiple nodes. That's what you're referring to.
We're going to get to that. We're going to go into detail on the architecture. Exactly, yeah. This is more about the NFS 4.2 spec generally and some of the parallel NFS stuff. And it's a little bit cart before the horse, too. It might be better to put this later, but yeah.
So in the component operations, right? Essentially doing the batch processing. You say, hey, do 1, 2, 3, 4 in that order.
Right.
If there is an error, so do you get to replay the whole thing, or do you...
So yeah, it's all built into the protocol on how, if you get an error along the way, what it does or doesn't process and how that works and how the return signals work. But it allows you to, it's kind of like a CISC versus RISC architecture, right? But imagine if the RISC architecture had to wait to fetch every command, it would be very, very slow. The fact that RISC can fetch a whole bunch, prefetch a whole bunch of the commands that allows it to be very, very fast. But what you've done is you've made, with RISC, you've made one bigger command by a bunch of little ones. So this is kind of allowing you to batch a bunch of RISC commands into a more sophisticated CISC command. Yeah?
So how much of the improvement that you're describing is due to changes in 4.2 versus 4.0? How much is just due to clients actually taking advantage of
In this case, with this specific stuff, I would say this is more about the fact that with Hammerspace, we've had the ability to build a file server, an NFS server from scratch that's designed to exploit all of these, as opposed to retrofitting it. So if it's a NetApp or an Isilon or any of those are kind of, they might have NFS 4 capabilities. Some of these things were introduced in NFS 4, like compounds, etc., but they were a retrofit, and it wasn't really tricked out to use it because it was still used. It was designed under the philosophy that I had to work with so many different clients, I need to be the least common denominator. But here, we designed the system to be highly tuned towards what's upstream in Linux. So I would say that on this first bullet item, the vast majority of this actually comes from simply being able to build a client and server that are able to truly exploit the potential of the protocol, not that it's necessarily new to the protocol. So good question. So the next thing, and this is something that was recently added. How many of you are familiar with the N-Connect or multi-channel kind of stuff? Tron helped drive that. TCP/IP is part of the problem with NFS. TCP/IP ramps slowly. It's very egalitarian. It backs off quickly. It doesn't really do a good job of flooding the network to get the most out of it. It assumes a congested network. And so one of the more trivial ways to overcome that is just make a lot of connections and feed the requests down those many connections. So it's kind of a way to not have to go to exotic, say, RDMA. And yes, NFS does support RDMA and everything, but people don't always have an InfiniBand or an Ethernet network capable of RoCE. So it's good to be able to get the most performance you can get from whichever network you're on. And this is one of the keys to that, is to be able to run many connections in parallel. And by the way, the requests can be sent down any one of those channels. You can distribute them. The ordering of the request, there's no guaranteed ordering once it's on the wire or anything like that. So you can actually just basically flood everything down and get responses back in parallel. And that helps avoid the problems. This allows us, by the way, to get 90% of the network's theoretical bandwidth over Ethernet without using RDMA. You go to RDMA and you can get 95, 98% kind of numbers, but that's pretty costly for just the marginal benefit. And this lets you get it without it. So it's an important thing. It's now built into Linux, and it'll work on any server, actually. That's a client-side thing. So just enabling the N-Connect option can often make a big difference. Now, one of the things that was important in the parallel NFS spec is the ability to write to multiple storage nodes in a striped fashion and in a mirroring fashion, so that a single file could be broken out across multiple back-end storage nodes. Remember, storage nodes speak NFS v3. We'll do some drawings in a second on that. But we introduced the notion to have that do simple synchronous mirroring. So now you can have storage nodes that are not highly available in and of themselves, and the client, through the coordination of the metadata server, can direct things to be written in redundant to multiple targets. So you can make an array of commodity servers reliable enough without any sophistication at all in the client. I mean, in the server side, in the storage node side, because the client is sophisticated enough to do that. Now, it does cost extra capacity, and some of the stuff that'll be introduced in future specs is to advance that to be using erasure coding technology as well from the client side. But this is one of the most important things to being able to make a software-defined infrastructure that is enterprise NAS, has that level of reliability you would expect. One of the other important features is within parallel NFS, the ability to spin up new instantiations of a file on another node while it's being read or written. If you had to wait for a file to be quiesced before you could move it across different nodes, then it would be very difficult to load balance. And one of the most important features is this: we can reroute the client's access to data in a fashion that doesn't interrupt its I/O. We can plug in a proxy that ends up routing to the same storage node while the client is writing. What that allows us to do is that proxy can then synchronize the creation of a copy, and you can then use the same technique to cut over to start using the new copy. So this allows you to do non-disruptive data mobility while it's undergoing I/O without so much as a barrier or a flush in the I/O stream. It's really important because NFS can literally have minutes worth of I/O in the queue. And if you had to drain that queue just to cut over and do stuff, then you've interrupted a lot of stuff. So this live mobility, the way to think about this, how many of you are familiar with VMware storage vMotion? Right. So you can move a VMDK while the VM is still running against it from one piece of storage. This is like that, but built into the file system, so I can move the data between those. And it does work under VMware, right? You could be running VMware on that, and it's like, well, now the storage layer is doing the vMotion for you. Yes?
So when you say proxy, it's still in storage mode. There's no client logic or any redirection.
So in this case, the protocol allows us to tell the client, instead of routing to this storage node to talk about this file handle, go to this other storage node and talk about this other file handle. Now, what the client doesn't know or care is that that's logically the same one. It's just you've put in something where it's a fake file handle that represents, a pass-through to the one in the back. That's what I mean by proxy. And in this case, it's not v4, it's NFS 3, because the way parallel NFS works, and I'm getting to the diagram now, I'm learning from this, I should flip the order. It has NFS 4 is an umbrella, but each of the storage nodes is just NFS 3. So basically anything that speaks NFS, and what NAS doesn't, that's the foundational protocol for NAS. So any NAS device out there is a storage node, one of many that can make up a parallel environment. So I can bring together multiple NetApps, I can bring together Isilons, I can bring together Cumulos, whatever. Anything that speaks NFS is a node in a bigger parallel environment.
Block storage?
With that, you can simply put a Linux head on front of it. We'll get to that. Yep. Let me jump to that now. Like a couple of slides, and we'll get there. The other thing we added, when you, in a parallel file system, you've split the control plane which is driven by metadata, from the data path. Now you have the data path in parallel, that's what gives you the scalability. But it also means you're not inherently aware of performance characteristics. When you split control plane from data plane, you need to have a feed on or a read on performance. So we introduced layout stats, which give you statistics summarized over small intervals of time about every I/O down to the specific file it's on. So we can say how much I/O is being driven to this specific file from this specific client, or to this other file from these other clients. I can roll it up very granularly. Last but not least is the additional work to make sure that NFS 4.2 is in every way a superset and capable of hosting SMB. So all of the Microsoft Windows ACLs and DOS attributes and those things and locking, those things can be served or mapped to NFS 4.2 from SMB, which lets you stack SMB as a front end on top of 4.2 in the back end. Okay, so this is what I should have done first. Simple architecture. It's really, you start with the metadata server, which we call the anvil. It's what has the directory structure, the file names, the access controls, the file system metadata. It's a map of all of the objects. But it, instead of giving the client, instead of servicing each I/O request, what it hands the client is the routing information. So the client can make its own connection on the fly and talk directly to the storage nodes, and do that in parallel. So I'll use 2 lines to show parallel. The data path is separate and separate from each other. It's perfectly linear scalable, as you would expect from a parallel file system. The metadata server never touches the contents of the files. It manages pointers only. What that allows you to do is this is now serving very small, latency sensitive things, while this can be serving very large. So if you think about it, traditional networked file protocols, SMB and NFS, are very broken at their fundamental level, because it's like having, the best analogy is having your DNS server have to proxy all of the traffic just because it resolved a host, to have to proxy the traffic to that host. In the file world, the server that resolves a file has to then pass all of the I/O traffic to and from that file. But in this model, it's more of a directory services model. The metadata server is handing out the routing information, the underlying IP. What it's called here is a layout. A layout is a map of where that file is found. A layout is stateful. The server knows that the client has the layout. It also represents a right to use that route, to talk to that file. So we're moving to where we're working with pointers instead of with direct routing. And that's what allows you to get to the scale. Any questions here? Yes?
So you mentioned you could put SMB, stack SMB on top of this, right? That I would assume would be on top of the Linux client itself.
Yes.
To make advantage of the...
It's 4 slides. Yep. That's exactly right. Let's go to the next one. So you asked about block storage. We're going to hit that one first. So if I have block storage of any form, NVMe, which of course, given Fusion I/O, I'm a fan of attaching it to the PCI Express bus, but it could be SCSI, ATA, fiber channel, doesn't matter. If you can, our DSX node turns that into a NFS v3 storage target. The DSX store, it's really Linux under the covers. XFS file system, kNFSD. There's actually nothing proprietary about that that's Hammerspace. As a matter of fact, many of our customers don't use Hammerspace software appliance here. They simply configure their own nodes to serve up their own block space as NFS v3 using kNFSD at scale. I want you to consider how cool that is, that not only with NFS 4.2, you don't have to have a proprietary client, but your storage node is also built into Linux. There's nothing special on the storage node or the client. The metadata service can literally just be on the control plane on the side. And that's good because you can't always control for, you can't always dictate a specific kernel or Linux distro or a specific software appliance. Especially with the big clouds and the hyperscales, they have their own kernels, they have their own stuff, and it would be better if it just was able to, at the lowest level, serve that. What this means, by the way, is that this is crazy fast. Because you can use XFS, kNFSD, you're gonna get full performance of however big a network you're gonna put on it, it can saturate it. Especially with the N-connect option, where you can get multiple connections, and the CPUs don't even break a sweat. It's very efficient of getting data out on the wire, and you're not gonna get more efficient than using kNFSD and, say, the XFS file system, which we like more than the others. So, okay. Any questions about how block storage is incorporated? And then the next thing is the data mover function, which is really just copying stuff NFS v3 to NFS v3, or NFS to S3, or any other object dialect. The metadata service, I don't draw it, but the metadata service has through control plane is directing his work. But so where this is the brain, this is the hands and fingers that get in and move stuff around. We're not using the NFS copy offload because that was spec'd, but the copy offload doesn't really give you the ability to manage load or know progress or anything. It's kind of a step too far. So we have our own service. And the other thing is this service implements that protocol we were talking about, where when the data mover is moving a file, it can service the I/O through to the file while it's moving. And that's also something you won't get from the copy offload that's built into the NFS spec. The other reason is that the NFS spec, the copy offload, only works between servers that are NFS 4 servers. And we want to be able to use just anything that's NFS v3 as the data nodes. And so this needs to copy NFS v3. We need to be able to flow control and manage its load and monitor its progress. And we need it to be able to facilitate live mobility of data. So that is a Hammerspace specific component there. And then last is what we call the portal function. You can think of it as a gateway. It is what can serve legacy NFS v3 and SMB, as well as S3 or any other protocol. You want it to serve FTP, it's sort of the same thing. All this is Linux with kNFSD and the kernel client. So Trond, our CTO, fixed Linux so that you can re-export an NFS mount. It wasn't previously recommended because it would deadlock the kernel and it would cause all kinds of havoc. But we needed to be able to use that so that we could take an NFS 4.2 parallel environment and export it as NFS v3. And so that is now actually built into Linux, and I know there are some companies that use it as a off-the-shelf NFS cache, because you can just set up a bunch of nodes that mount your NFS file server and re-export it. And what you get is that the page cache in every single one of those nodes gives you huge amounts of data being cached. So it's you can amplify the performance. So think of it like oh, shoot, I just lost it. The company did NFS caching, acquired by Microsoft a while back. Avir, thank you. Yeah, I should know because my head of sales was head of sales at Avir. Thank you. That's now, that capability is actually now available in Linux off the shelf. You just mount an NFS file system and export it. Now it's not as sophisticated with all the glue, but basically it works. We use this technique to take, the mounted file system, export it as SMB or as NFS from there. And this gives us sort of, now anything that's file, block, or object, data can be stored on anything file, block, or object, and we can serve it out. Notice I'm not serving iSCSI or fiber channel SCSI. You could take files in this file system and export them as block devices, but we view that as kind of looking backwards, except for in the container world, because then it just becomes a loopback mount of a file. So we do actually serve container storage interface to block devices, but those block devices are just files on an NFS 4.2 file system. So we are serving block, file, and object, but only block when it's on the same node like a container node. And we have a number of customers who are using us as the storage under their Kubernetes cluster environment because it allows them to serve all different forms of persistent volumes. Shared files, systems, local block devices, a file system in a local block device, all types are now part of this, and the data can be moved non-disruptively across the thing. Now, do we read directly from the disk? So, if the, well, let me go to the next slide here. These are all internally just Linux. This is really purely Linux. This is a service that stacks on top, and this is maybe KNFSD, or we do use Samba that we've had to beat the hell out of to get it into shape. I'm looking forward to when the kernel Samba server is in better shape. But if you look at this from a, all of that's running on, say, one node, and it's just a Linux node like the other. So it's doing the data moving function, it's doing the sourcing function, it's doing the bridging function, all from Linux. And oh, by the way, since this is just Linux, those can be deployed as services, systemd services, or in a container if you want, on your Linux nodes. Which means that your Linux nodes can host local storage and have that local storage be part of the big shared file system. In other words, a hyper-converged model. And, as Gary was asking, if the data has been placed onto storage local to the same node that happens to be consuming that specific file, then enhancements that we added into the Linux kernel allow it to short circuit. It's kind of like it realizes, I'm an NFS client, and I've mounted an NFS server, and it's me. I'm the server serving myself. So why do that? I should just go through the VFS layer and pass the buffers. Well, this works when the data is co-local to the client that's using it. And with our ability to move data, we can position it such. And with our ability to mirror data, we can, for example, make sure that the writes happen to a copy on the node and on another node or in the back. So we can write redundantly off node and on node, and we can favor reads locally. So you can say read from the local mirror, write locally and remote. And with the data mover able to move things around, you can position it that way. Of course, the data mover itself is a service, which may or may not be on the same node. It could be the metadata server could coordinate it such so that it is on the same node. We don't yet do the bypass stuff when the data mover is plugged in. It's some of the enhancements. This ability to plug in a proxy in the data path to do the moving and or erasure coding, we're talking about enhancing how it plugs in so that it's not just NFS v3 in and out as a proxy, but when it's co-local, it can live in user space and get the data buffers directly. So think of it as being able to pass the data buffers from in-kernel out. This isn't like the fuse file system because this is just the data path pieces. The metadata is still going to the metadata service through a typical way. But that would allow you to get some of those protocol bypass benefits. Okay, to make it even more complicated, the Anvil and the DSX nodes running in one data center can replicate to the metadata service, the Anvil, in other data centers and create an eventually consistent unified global namespace to where it is the same file system being presented everywhere. And with the ability to move data, we can shuffle data between sites, keeping it redundantly at the different sites, and now data is able to be omnipresent across different data centers. Such that if I change it in this file system, the metadata gets replicated, he's aware of the change. If he goes to access it, he's going to fetch the newest, latest version of it. But these are separate first and unified second, meaning each data center is a self-standing file service. Metadata and data, storage nodes, unified namespace. You could sever the connection to the rest of the cluster, and this is able to serve at least anything that it already has data for. And you could go on days, months at a time with this separated. Plug it back in, it'll resync the metadata, and the data can then flow in and out. In other words, it solves the issue of edge computing and the need to work with intermittent operation. So the protocol, we tried to learn from failed attempts in the past at doing multi-data center file systems. They tend to be too tightly coupled. So this is decoupled first and coupled later. We don't try to propagate locks, although that could be added on as an additional layer. It's eventually consistent with collisions being disambiguated. Meaning, if I create the same file in the same directory at the same time, or while he's disconnected, that get created over here, then it will render the other guys with a suffix that says from the other site. So each site can have their own version of the truth, which is unperturbed, but when they're unified, or when it's viewing them together, it'll show the other guys with the qualification of what site it came from. In other words, collisions don't exist because you can always surface enough disambiguating information to be able to show the difference. That's for the namespace. In the data space, if this guy writes to a file and he writes to the same file, we're not solving the speed of light here, it'll create alternate versions, and when they unify, one will be a prior version versus the other. Last writer wins, other writers show up as previous versions in time. In other words, we can always disambiguate either in space or time so that there is no such thing as coincident across the environment. Yeah. So the data centers are all running Hammerspace componentry that's rendering the file systems. Yeah. And that allows you to have active-active. We have, for example, customer Epic Games, who has like 15 different data centers, all sharing the same file system on top of NetApp. Yeah. So this is extremely scalable. This is detailing just a 16-node cluster. We have customers that are doing upwards of 1,000 nodes in a cluster, at which has 100 terabits of networking performance, of which they can achieve 90+% of that. So this is a scale that you wouldn't see except for in the world of the exotic parallel file systems like Lustre. And the beauty is it's not it's not Hammerspace on the storage nodes or the clients. They're using their Linux on the storage nodes, their Linux on the clients. They've just configured it to serve NFS v3 and added all that to the environment. Yeah?
How does your metadata service scale? I can understand the data part.
Well, number one, it gets a huge advantage because it's only working with metadata. You don't have to swallow an elephant to get to the little sugar cube you want to. So just the decoupling is a major advantage and allows us a certain level of consolidation compared to other NAS systems. But it is still something that we are in next generation building a fully scale-out service, because at that point it becomes truly unlimited.
So what I meant is for workloads which are metadata intensive.
Yeah.
There you would
Yeah.
expect.
So the interesting thing there is, because this is a software overlay, you can easily multiply instantiate it. Those are different file systems, but you can get additional quotient of performance by just making another instantiation. So unlike something that is the storage and you have to host on it, this is something that I can make as many instantiations and add as many processors as I want to it. But you do have to compartmentalize. This file system has its performance, this one has its performance, this one has its. And one of the benefits of 4.2 or NFS 4 are referrals. You don't have to worry about auto mounter and all of that. You can have many different file systems in a single structure that looks like a single file system. The system will automatically open and navigate them. This is showing, one of the things I'm most proud of is that Jeff Bezos' own Blue Origin is using Hammerspace as their way of doing hybrid cloud. So Hammerspace at each of their 5 facilities around the US, plus in the cloud. And it's Hammerspace that allows them to have the same file system presented where they design the engines, where they manufacture them, where they test fire them, where they launch the rockets, where they monitor the rockets in space. All of that is, has the convenience of just being the same file system. But one of the reasons why they went with Hammerspace is because this allows them to solve the challenge of data in space with super high latencies and intermittent connectivity. You need something more sophisticated than just a caching or something to stretch data between sites. It has to be able to do it on a schedule and proactive as well as reactive. So this is really a prototype of what it would take to be able to offer IT services in their orbital reef space station, a business park in the sky. To support that science, you're going to need IT infrastructure there. Having the same file system will make it really easy. So, summary, NFS 4.2 takes parallel NFS that was designed sort of single purpose around performance, and we're using it not just to get the high performance, but also the flexibility of incorporating storage of all different types, file, block, and object. And be able to orchestrate data across those. It enables us to move data while it's live. So basically have everything everywhere all of the time. It doesn't necessarily have to have everything copied everywhere, but it can move things based on policy or based on demand, so it gives you the appearance of already having everything everywhere. And it's able to serve that at that highest level of performance. Yeah, and it's built in. And it also supports all of the snapshots and clones, audit, antivirus, all the stuff you'd expect from enterprise NAS at the same time. So, yeah. Mm-hmm.
But I think you explained that the copies that we maintain across the sites are not consistent.
Yeah. So we have a mode today where you can do file reservations, which is kind of a proactive locking. Allows you to lock whole directories and stuff. Because the main model is to have people simply, you don't want to run the same application using the same files in two different data centers, right? So it presumes a sort of a higher level coordination on it. But if you want to, for example, allow some users to go muck around in these directories and not accidentally stop on other users, then you can use reservations. It's kind of a more loose or explicit locking mechanism. You could conceivably overlay a locking system, but then you would start cross-coupling your sites to be interdependent. And I've been very surprised to find most folks aren't looking to try to abuse a system like that. They just want to have the data where they need it and are happy to coordinate when different apps are active on it or not, or when different users collide with it.
Also, the application, are you going to keep like any number of copies per day or like based on size if you have?
So the replication, I mean, we also have snapshots, and those snapshots have their own policy. The snapshots can get orchestrated, so you don't really need to back the system up because you can just stick it off into Glacier with object block from which you could reconstitute it. So backup is done sort of within the file system, not as a separate thing. Think of it like Snap Vault, but able to go across third parties in a self-contained fashion. So yeah. Additional questions? Yeah.
Yeah, on the same topic. So the replication, does it make use of any of the vendors' replication? Let's say you're using NetApp.
So we use the offloaded clone,
Okay.
so that when you do snapshots and clones at our level, we can defer the copy on write down to them. It's really the only piece that you need because everything else is just sleight of hand in the metadata. If it doesn't support cloning, then we will make a copy. And if you already have copies made, we call it King Solomon, it'll just say, you go to the old guy, you go to the new guy, and I'll start writing to the new one. So there are ways to work without the offloaded clone. Mm-hmm.
File-level clones or
Yeah.
file system?
Not only file-level clones, but you can do a recursive copy of an entire tree in the background while you're using it. In other words, you can make it look like you've instantly copied an entire tree. Yes?
A couple of questions on the metadata server. Is that like a point of failure in the sense that container or whatever goes down, what happens to file access?
So it's n-way redundant, and it has checkpoints that are backed up from which you can restore, and you can periodically dump to text the pointer map.
But if all that went wrong, you would lose access to your file.
The data itself on the storage nodes are just numbered blobs.
They're just numbered.
Right, there is.
The other one is, can you give us any sense of the capacity requirements of the metadata server? Capacity,
So 4K per inode is generally, even this because we're using a KV store where the inodes are actually generally much more compact than the standard 4K from the Unix world. But we say 4K because it has to have space to do compaction and other stuff in the KV store. Yep. Happy to answer more questions out or after. I'll be around. Thank you.